With this bell work, we are looking at a computer printout. This is just as a basic thing to keep in mind. If there is a computer printout, it is going to be a regression question and not always going to be an inference one. But this one is, because you can see we have a couple of, sorry, I'm not writing yet. We have a couple of hypotheses. Luckily, we're not having to do anything too complicated with this problem. It says, what is the p-value for a t-test with these particular hypotheses? Just to answer this question, remember that computers always calculate the p-value as a two-tailed test. So if it's a one-tailed test like we have here, then we need to take the p-value that's given. We never care about the constant or the intercept, whatever they call it. So I'm going to cross that row out. So I'm going to take the p-value. Notice it says prob, that's probability, same as p-value. It's always after your t, your test statistic right there. So anyways, 0.0478, I can divide that by 2 to get 0.0239. So your answer is B. Now, for those of you who were not here, maybe only one of you, but also for those of you who were here, everything that we need to know is found in this printout. Our test statistic is B minus beta over, let me write it a little better, S sub E divided by S sub X times the square root of n minus 1. And this is essentially your standard error. So if I wrote it this way, B minus beta all over your standard error. Well, your B is your sample slope, which is found right here. And you've been finding that since unit 3. Your standard error is right here. And your beta is 0 because that's the null hypothesis. So if you weren't here and this is the first time you're seeing it, linear regression inference is actually pretty straightforward because I can just take the 0.573 ... divide it by 0.2312, and we will get, the calculation's even already done for us. We get 2.48 as our test statistic. You can actually plug that in your calculator, make sure it's true, but it is. And then we can use TCDF to calculate that right there. But the great thing about it is that we don't need to do that if all this is already given to us. So we just saved ourselves a bunch of work. And even right here, it doesn't say our sample size, except if we look at it, we can see the degrees of freedom right here. There's n minus 2 gives us our degrees of freedom. So everything that we need is right here. This right here is S is always S sub E. And it's important to remember S sub E is different from SE. SE is your standard error. S sub E is a sample standard deviation of your residuals. So that 4.136 is the average difference there is from the predicted value. Okay, now if this was a confidence interval, and this one is not a confidence interval, but if we had the same data and they wanted us to create a confidence interval, that'd be B, which is your sample slope, plus or minus your T star critical value times the standard error, which is S sub E over S sub X times square root of n minus 1. And again, in our case, B is already given, it'd be 0.573 plus or minus whatever T star value we have. That's a plus or minus right there. Whatever T star value we have times 0.2312. Yeah.
So could you explain the difference between those two tests and what they find?
Yeah. So this right here is your confidence interval. And what this is going to be telling you is it's going to give you an upper and lower range of what the expected slope for the population would be. Now, with our sample, we got a slope of 0.573, which means that for every increase in, okay, versus price of the best seat. So it looks like attendance is being predicted based on price. Okay. Okay, so basically there's the idea. I'm reading the prompt here. So the idea is that if you actually price your tickets higher, you're going to get higher attendance, which is a strange thought. So as it is right now from the sample, we see the 0.573. So for every dollar that you increase the price, you would expect 573 more people in attendance. So the 0.573. But that might not be true of the population. That might just be true of the sample. So what is the true value for the population? We think it's going to be somewhere between the lower bound of our confidence interval and the higher. And we could figure out what it is, but essentially we'd have to know what T star we're going for. So if there's a 95% confidence interval with 6 degrees of freedom, then we could figure out the T star and go from there. But let's say that we have a low end of about 0.35 and we have a high end of 0.79. So somewhere between, I'm making this up, okay? But somewhere between 350 and 790 people more are going to show up by increase the price of $1. And I'm getting the 350 versus 790 because these numbers are in thousands. Does that make sense?
Yeah, right. And then how does, so what is this?
The test. The test is, so that's the confidence interval. The test says we want to test whether there's actually an association between these two or not. Is this slope here due to random chance, or is it there because there's an actual association?
So this one is for to test the hypothesis.
Yes.
And this one,
Yeah, we got it. And that's good. That's a good question. So again, just to wrap up with the hypothesis test, because our null hypothesis is that there is no association, we're going to have to get a slope that is really big compared to the standard error. So we can get a bigger test statistic and therefore a small p-value in order to determine, no, there really is an association. This wouldn't just happen by random chance. Okay.
How come you divided by?
All right, so for the rest of today, we're going to be doing some practice. And what does practice mean? A bunch of these. Okay. So maybe what we'll do is I'll let you look at this and I'll just kind of run through the process for the problem. This one's actually pretty straightforward. Even not reading the full problem, I can see that they give us a regression equation that involves a transformation of data. And they give us an X value. So I'm betting that I need to plug that X value in and solve for Y hat. Okay, so see if you can do that. I will circle my answer in just a minute. See if you guys agree. So just to go through this one real quick, I'm not going to spend much time on it. If I plug X, 4.8 in for X, the right side evaluates to 0.1. So I'm going to get the log, apparently, the log of Y hat equals 0.1. And what we need to remember is that to get Y hat on its own, we're going to raise E, not E. It's going to be 10. So the log, I cannot write this. I don't know what's going on with it. So the log and 10 cancel each other out. So Y hat equals 10 raised to the 0.1 power, which is 1.26. D is the correct answer. That was the most common one that was answered. So that's good. All right, let's try another one, eh? So go ahead, just give this one your best shot. I'm not going to spend as long on this one, and then I'll explain what the answer is and why. With this problem, we are, now what is a safe bet for this is because this is a whole unit on linear regression, you're maybe just as a default bet, you'd go for this one, which happens to be right, but I want to explain why it's this one and not any of the others. So this could very well be a matched pairs t-test. And we could imagine all kinds of reasons why we might pick one versus the other. The thing that makes this a linear regression test is because we have what is however many participants this is, 10 participants, and there's two variables associated with them. Again, we could get a difference, the percent before and after, body fat percent before and after. And then this could be a matched pairs where we get the difference. So we could get the, eventually we get an X bar sub diff and all that fun stuff. But we use a matched pairs test if we want to determine what is the average weight loss predicted, like if that's a confidence interval, what would the population lose on average? Just in general, not making any predictions, but what in general would someone lose? And then we could determine if it was an effective program by using a hypothesis test. Is this the kind of body percent or body fat percent loss that we'd expect if this was an effective program? Is this through random chance or because there's something more to it? So the matched pairs lets us determine if this change is statistically significant, but it doesn't let us predict what the body fat percent for someone who completes the program is going to be. So what we're trying to figure out is the true slope, because we want to figure out if you knew the body fat percent before, what would you predict their body fat percent to be after they're done? So we're trying to predict the correct slope. And so, and since we're trying to figure out whether this is statistically significant, we are doing a linear regression t-test for slope. And the null hypothesis, of course, is that there is no association. But if we get a statistically significant result, that means that there really is some kind of an association, and therefore we can draw some conclusions. There we go. I don't know if that fully explained it, but we're dealing particularly here with the slope in this prediction question. So this one right here, almost all of you should be able to kind of look at this and determine what the 95% confidence interval will be. And you can at the very least rule out some that are not correct. See if you can come up with the correct one. I'll relaunch the poll. Okay, so with this, we are looking at this row right here. Let me go ahead and mark on this. We don't care about the constant for linear regression. So it's going to be our B plus or minus the T star times the standard error. And we already have those. The standard error is right here. It's going to be 0.04625 plus or minus the T star times 0.01565. So that helps narrow it down a little bit, but we still have three choices. So the real question is, what's the T star? And a lot of people were saying 2.96 because you saw this right here. That's actually your test statistic if you're doing a hypothesis test. So it's not that, so it's not this. Right, that's if it's a Z star. But for T star, because our degrees of freedom here, we have 16, so it's going to be 14 degrees of freedom. 95% is 2.145. Your answer is A. All right, but that's good. We're seeing it. We're making these mistakes here, and we're not making them later. All right, and you can pause me at any point if this still isn't making sense, if something isn't clicking. Or just flag this question. You can ask me about it later. Okay, what's going on here? We're going to, hey, we have another similar question. So find the expression that will give us the 95% confidence interval for the slope of the least squares regression line. All right, same thing as before. I will launch the poll in just a second. So since everyone was in unanimous consent that this was A, I don't think we need to spend too much on this, but that is correct. And notice they give you a lot of things that might convince you that it should be one versus the other. So if you're not thinking clearly, you might look at this. That comes from your S divided by the square root. That would be something if you were convinced this was a one sample t-test or something like that, or one sample t interval. but that's just a distractor on there. They give you your standard error right there. You're good to go. So don't overcomplicate linear regression. If you see this printout, just kind of immediately tell yourself, this is going to be something really simple. I just need to find the right number to plug in. Okay, let's look at this. Meteorologists are interested in the relationship between minimum pressure and maximum wind speed of hurricane. The minimum pressure in millibars and maximum wind speed in knots were collected for a random sample of 100 hurricanes from the year 1995 to the year 2012. A regression analysis of maximum wind speed on minimum wind pressure produced a 95% confidence interval of that for the slope of the least squares regression line. Which statement is a correct interpretation of the interval? I'll let you guys think through that one. Everyone thought the answer here was C, which is correct. And what we want to remember is that the confidence interval is predicting a slope. And this is an association between minimum pressure in millibars and maximum wind speed. If we have a negative slope, that means that as one increases, the other goes down. So as minimum pressure increases in millibars, we would expect the wind speed to decrease by somewhere between 1.2 and 1.42 knots. So at the very least, I'm sure you could have narrowed it down to these three, and maybe that's where you got lost, so we can rule those two out. Okay. How many more of these do we have? I don't know. We're just gonna keep having fun. All right, another question on confidence intervals, 98%. So you can go through this problem again and see what you come up with this time. Again, this is very much like one of the first ones we saw, where they give you three legit or three possible answers, two of them that we can rule out right away because we don't care about the constant in any of this stuff. We're always looking at the slope. So the real question is, what's the T star? And our degrees of freedom, since there are 22 observations, is going to be 22 minus 2. So we always subtract 2 degrees of freedom with linear regression. So it's going to be 20 degrees of freedom, 98% confidence level, which becomes a 2.528 T star. And that's where we get our confidence interval. Okay. Now we'll clear that. Let's try another one. Here, I want to see something. So some of these are FRQs, and we're going to go through those. So now we're on this one right here. You know, this one's kind of more of the same. I will skip that one. You can come back and look at these. You can try that one on your own. But here, I'm not going to read this, but the question is, what's the appropriate conclusion for the test? So read through this and see if you can come up with the correct answer. This one takes a little bit of reading and kind of thinking through. There's some of them that we might be able to rule out pretty quickly. If you're not sure about why we'd rule these out, I'm going to go ahead and rule out A and B, because the p-value does not relate to what those we're talking about. This last one indicates that the scatter plot is likely due to chance. Actually, it means the opposite. If a p-value is less than 0.05, which it is, then it's not due to chance. There's probably something else going on. So the difference between C and D is that in C, it's saying that there's an association between lean body mass and higher maximal oxygen uptake. With D, they're saying that there is a cause and effect relationship. So we're not talking about cause and effect here. We're talking about an association. So the answer is C. Okay, so if you didn't catch the nuance there, then maybe you can see it now. All right. And let's look at this to determine which condition appears to have been violated as far as doing any kind of inference tests for this data set. The answer that I came up with for this was E. All right, and the reason I picked E, and the reason this one is correct, is because what we're looking for in our residual plot is, now it's not phrased the same way that we might expect it, but we want constant variance. We can see there's a lot more variance on the right side of this as we get higher in height than there is on the left side. So this instead takes on a shape that looks more like this. So this, we would just say, oh, it doesn't have equal variance. But we need to see the condition that we're looking for is that there is equal variance the entire length of the scatter plot. But what is violated is this condition that should be met. The variance of the response variable is constant for all values of the explanatory variable. This might not immediately make sense as though it's talking about the same thing, but remember your explanatory variable is your x value. So for all x values, you are looking for the same kind of variance, something like this. But if instead it goes like pretty tight and then it scatters out big time on the right side, like this one might, then we don't have equal variance in our values as we move left to right. Does that make sense? Okay. Fun times, huh? So that's where we violated that one. Now we're looking at this. This is a test statistic. Sure, let's just do this one real quick. Hopefully you can figure this one out before too long. Our test statistic looks like this: b minus beta divided by, I'm just going to write standard error because the actual equation doesn't matter. Our beta is always a 0, so it's just going to be b divided by standard error. And b is given right here. We don't care about the constant. So it's negative 2.20 over standard error is 0.07. That's given right here, d. So if you were overthinking it, next time underthink this one. Okay, so it's really not that bad with linear regression. I'm gonna go ahead and clear that. Now we have a couple of FRQs. Let's see if it's worth looking at this. I'm kind of going in reverse order real quick. So the first one, I might or might not do it. You can kind of stop me if you do want me to go through the full process. But it asks you in part A to construct and interpret a 95% confidence interval for the slope of the least squares regression line. So not only do we need to construct it, we need to interpret it. I don't care about the constant. So my confidence interval is just b plus or minus the t star times the standard error. And those are given right here, b and standard error right here, and t star. So we have to look that up, but we have a random sample of 20. So it's going to be 18 degrees of freedom. And we're looking at a 95%. So 18 degrees of freedom, 95%. Looks like that's a 2, our t star will be 2.101. So we have the numbers to plug in. All right, you guys can find that. So I'm not going to actually do that. Well, actually, I remember this question. So let's go ahead and do this real quick. Let's come up with our confidence. I wanted to talk, I think we need to know that in order to answer part B better. So it's going to be negative 2.158 plus or minus 2.101 times 0.149. All right, I'll pause the recording and we'll just come up with that confidence interval real quick. All right, so I kind of just jumped into this without even looking at the prompt. I mean, that's kind of bad of me. I should know what it is I'm even solving for and why. But this is a confidence interval, and now let's kind of put it back into context. So a real estate agent believes that for 3-bedroom houses, the selling price of the house decreases by approximately $2,000 for every mile increase in the distance of the house from the city center. To investigate the belief, the agent obtained a random sample of 20 3-bedroom houses. The selling price in thousands of dollars and the distance from the city center for each of the 20 houses are shown in the scatter plot. The table shows computer output from the regression analysis of the data. So does the confidence interval contradict the agent's belief about the relationship between selling price and distance from city center? Let's interpret this real quick, because I didn't actually interpret it for part A. So our confidence, so I could say we are 95% confident that the cost of a house decreases by somewhere between, well, I could have phrased this differently. I could have said, we're 95% confident that the interval from negative blah, blah, blah. But anyways, this also works. That the cost of a house decreases by somewhere between $2,471 and $1,845. Remember, the dollar amount is in thousands of dollars. So it's going to decrease somewhere between this amount for every, that's every mile from city center. All right, so that's my interpretation from part A. So if the agent believes that it's $2,000 for every mile increase in distance will decrease it by 2,000, does that fit in our confidence interval? Is that in our confidence interval or outside of it? It's inside. So there's a 2,000 for every mile increase. So the decrease is 2,000 for every 1 mile increase from the city center. So this, our confidence interval does not contradict it. So we can write something to that effect. Because the $2,000 per mile is within our confidence interval, we have not contradicted this agent's belief. Okay. And one last one to go through. So I did this a little bit backwards. So in this one, state the equation of the least squares regression line for these data, define any variables used. So they just want you to actually write out your y hat equals a plus bx. And these, you got your a right here. And this is your b. And we want to define that. Okay, I'm actually not going to do that. If you want to go through it, then try this on your own. If you can't figure it out, come back to class on Monday and we can go through this one. The next one asks for a 95% confidence interval. Well, it already has it calculated. They calculated a 95% confidence interval for the intercept, but they want us to do the same for the slope. Okay. And this last one is where it gets a little bit challenging, perhaps. The company wants to know if charging a flat fee of $3 and a mile and a per mile charge of $1.50 will maintain its current revenue. Based on the information in part B, is a flat fee of $3 a reasonable value? Explain. So how about you guys give this one a try in your own time? Maybe we'll go through it on Monday if you guys want to. If you feel like you can do this one and you're confident with your answer, then you're good to go for the test on Monday. All right. In the meantime, I encourage you to go through those progress checks that have been assigned to you. They're available in AP Classroom. Finish your Unit 12 homework so you can just get a little bit more practice with it. And this is the last unit. This is the last stuff you need to learn for this class. So we're going to start with that review soon. So have a good one. If you have any questions, stick around. If you're good to go, then you enjoy your weekend. I'll see you on Monday.